Hello, AP Statistics. Today we're going to learn another inferential procedure in order to conduct confidence intervals and hypothesis tests. So you should have in front of you the example with this set of data over here where we have a variety of employees. Do we know where they work? Lake County, Illinois, and these are health department employees, so they must involve, their jobs must involve a lot of driving around for various health department purposes, like checking if restaurants are healthy enough and stuff like that, maybe closing them down if they're not, if they find too many rat feces or something. So we wanted to compare a 5-day week and look at the mileage those employees accrued. We're going to assume that they kind of accomplished their job either way, versus the mileage they add up over the course of a year with a 4-day week. So of course these numbers are the miles that they're driving in 1 year. They have some kind of special odometer to record that over the course of a year for one work week versus another. So really this is being conducted over 2 years, isn't it? How do I know that?
Because there's one more for each.
Because it's the same employees. How else are you going to get two different numbers for the same person? So this, I think, really illustrates the value of spending a lot of time before you just jump into a problem, thinking about all the different little intricacies or nuances of the data. What do you know? Spending a lot of time on the W's that we went over at the very beginning of class. That can really save you from applying the wrong inferential procedure. Because it'd be real easy here to look at these and be like, well, those aren't proportions, right? They're not percentages. They're just numbers. They're just averages, right? And apply a inference procedure or hypothesis test for two means, right? It'd be really easy to jump in and do that. But the reason we don't want to do that is because, of course, these are the same person and it violates that fundamental independence rule.
You messed up on the table.
Where at?
The last two.
Where am I at? So,
You skipped
Yeah.
Leslie and then you
Yeah. That
Right here?
number's for Lee.
thanks. So I'll fix up my data set real quick. Thanks to some live students. And we'll start. So, the inference procedure we want to apply here is not for two separate means, but for paired means. So this is a paired test. So let's make sure we write that nice, vibrantly in our notes somewhere that it can fit. I don't know, maybe over here. But this is a paired t-test. I guess I had that right here, right? So a paired one sample t-test. It's a t-test. Why? Can you guys tell me? Why is it not a z-test?
We're not given a standard deviation.
We're not given a standard deviation. If we were given a standard deviation, that would of course work. I don't know how in the heck you would just know the population standard deviation here. It's of course completely unrealistic. Why else is it not a z-test? Just kind of obviously, because we're not doing proportions, right? So we know it's going to be a t-test. So what's our population of interest that we're thinking about?
Workers for the health department.
Workers for the health department? Anybody else who want to extend these results to?
All health department.
Maybe? Do you guys think we want to just be thinking about this health department or all health departments?
Probably this one.
Probably this one. Like this company is running this research, so I think, I don't know, workers at, you know what, if I wanted to be real careful, I could always use that cop-out. Workers at health departments,
Like these.
like these. Now I'm extra safe. So what's my variable of interest? Not real hard. Mileage, if you're being pretty general. Mileage at work, not just like all the time they spend driving on their personal time. And again, we decided we didn't want to look at them separately, so it's not just mileage at work, it's mileage at work and the difference between the two schedules. So you might not catch that right away when you're doing a problem like this, but as soon as you realize that the data are fundamentally not independent and paired for some reason, like a pre-post or a 5-day to a 4-day week, there's all kinds of ways they can be paired. You want to work that in wherever you can. So what do I know here? I know n. How many is n?
11.
11. And then I don't think I'm either going to work with this set of raw numbers to get the average statistics I'm interested in, or that one. I want to find the difference between them. So of course I'll use my calculator to create that. So I'll get the rest of my statistics from my calculator. So enter your stuff in your lists. I've had some fortunate assistance from my students here. So I've got the data entered, and then over here in list 3, you can just subtract. So we'll just go and do, it doesn't really matter which way we subtract. We could go list 2 minus list 1, or list 1 minus list 2, works either way. So there are the differences, which we could put over there as a separate column if we wanted to. But I think I'll just go ahead and run one variable statistics on list 3. And get what I know. So there's our 11 sample to compare. X bar, you know what? I'm going to subscript it with something to really demonstrate or exhibit that I'm doing a paired test. What letter might be a good word here for a paired test? P is not a good letter. Why? We've used P for a lot of things, like p-value and proportion and p-hat. Oh my God. Let's say D. I don't think we've used D yet. D for differences, right? So X bar sub D is negative 982, and these are miles, right? And I'll also get my sample standard deviation, S sub X sub D, and that will be 1139.57, something like that.
If you did list 1 minus list 2, would the signs change for those?
Yeah, this would probably be like positive instead of negative, but this shouldn't change, should it? The spread should remain consistent, regardless of which order you subtracted.
Yeah, I don't know what I did wrong, but I had like totally weird numbers.
Well, I didn't check the data. Do you guys have about the same?
Oh, it's
I have-
one variable
that's the
stats
same
of
thing
list
I have.
3, not just
Yeah.
in general
Oh,
of list
list
3.
three.
Yeah, you got to do one variable stats of list 3, right? So if you didn't do that, you might have an
Oh, I did a
issue.
typo.
You might have a typo as well.
Yeah.
So what do I want to know here? I really want to know, just like always, a parameter. And this parameter I'm interested in is the true average difference, right? If the true average difference is close to 0, then there's not much of a difference between the work weeks. If it's not close to 0, then there is. We'll just have to see. So I want to know the true average difference. And I'll just go ahead and put my hypotheses there as well. You've got the procedure as a one sample paired t-test. So let's put our hypotheses down here as well. Just like normal, H sub O, H sub A. Can you guys guess what symbols I'll be using here though? A mean, so we're going to use mu, regular old mu,
Subscripted?
mu sub D for differences. And I'm going to assume that that is 0, but there's no difference. And what do you guys think? Should we do a one-tail test, a two-tail test? And if it's a one-tail, which direction? Do I want to go greater than, less than? What are we interested in looking at here?
Well, I think we should do a one-tailed test because they're only looking, because they want to see.
You can go back and read the question, right? So in our question it says, for a year the department recorded the mileage driven for the ordinary 5-day week, and then for the next year they looked at a 4-day week. And it says, I don't know, does it say anything else?
I think they say, do flexible schedules reduce, like in the bold part at the top. That's what makes
Do you
me
guys
think
see
it's
that?
one-tailed.
The very title of the question is, do flexible schedules reduce? Kind of like if we were on a school day, right? Does the 4-day actually reduce something, right? So the idea here is that the flexible schedule is the 4-day week, right? Does that actually reduce mileage? Which you might think it does because you're at work less amount of time. It seems like it probably would, right? So does that mean this needs to be greater than or less than? It's one tail. That says one tail, not two tails. Greater than or less than. You could go back up here and look at where this came from. It's negative, right? And I went this minus this. So this minus this this minus this, this minus this. What do you guys think? Which way? Less than or greater than? You could also just like look at that being negative and go, I think I'm interested in that. If you did it the other way, yours would be greater than. The way that I have it, it's like that, okay? So, my assumptions, let's go and look at those. SRS. What do you guys think? Randomization.
Well, I don't know.
Is it a random sample?
They never said.
They said an ordinary.
I don't think so. Because, like, this is kind of, like, gonna have to be voluntary in some way, right? People probably aren't gonna, like, just say, okay, now you're 5 days, now you're 4 days. So we're just gonna have to assume that these employees are representative of the company. Hopefully they chose a nice broad representative sample. We really don't know. That could be dangerous. The population, we know what the population of interest is up there. Population of employees at a health department, if this is like any kind of size of county, should be good. We're looking specifically if that's bigger than how much? 110. I'm going to say sure there are lots of employees. This is America. We like spending lots on bureaucracy. America. Bureaucracy. Yay. Not being political at all. Let's see, what else do we need to check, do you guys think, as an assumption for this kind of procedure? What needs to be nearly normal?
Difference.
The difference. So let's go ahead and get our calculator and investigate that. So I'm going to go and you could look at a variety of things. I'm going to talk about a new technique that you might actually use today. Let's look at the histogram first, though. So we're going to go and make a histogram of the differences, right? So we're going to look at that histogram and see what it looks like. Turn this other one off. And there's the histogram. It doesn't look bimodal or anything like that. It might be a little bit skewed this way, but it's not terrible. I can mess with the bin size a little bit. The bin size isn't going to have too much effect here because we only have 11 pieces of data, right? So we could play with it a little bit though. Maybe go like 700, something like that. I'd say that that's nearly normal. There's no really big issues here. It's not perfect. Another way you can assess this besides a histogram that I thought I'd just throw into this video is something called a normal probability plot. I don't know if you've ever used that. So let's go back and create a new plot. If you go to second stat plot, you can also go to this very last option in the list. I bet you thought this was just a line graph. This is actually something called a normal probability plot, which has a lot of different uses. One of them is just to check this assumption, basically. That's the reason it's usually included in calculators like this. What a normal probability plot does is it basically standardizes, it turns everything into like some kind of z-score type thing. And if the plot is pretty straight, your data are pretty normal. You can see that this one's got a little bit of bend in it and stuff like that. I guess I should have hit zoom 9. But it's not terrible. It's reasonably straight. It's not like super skewed like something like an ogive or something like that that's really bad. So that kind of confirms what I saw with my histogram. It's not incredibly normal, but it's approximately normal. So we'll go ahead and say that in our assumptions. So the histogram or normal probability plot of differences is approximately normal. Got to use that approximately, otherwise you're going to run into trouble, right? Okay, so now all we've got to do is find the test statistic. That's going to be the easy part. So we decided that it was a test statistic already, and it's going to go just like always, except it's going to be x bar sub d minus mu sub d over, what do you guys think? Standard deviation, SXD. Anything else? Oh yeah, don't forget that square root of n. So for us, t is going to be, whatever it is, negative 982 minus 0, which is the hypothesized value we're checking, over 1139.57 divided by the square root of 11. Come up with what that is. Got about negative 2.85. And degrees of freedom, what do you guys think on that? How many degrees of freedom?
10.
That's right, and minus 1, just like usual. So we could go to our table with 10 degrees of freedom. I'm going to go ahead and get rid of the data over here just to save myself some space.
I have a question about our assumptions. What if, like, how would we assume that, like, what if this is, like, what if, say, Tom, he got a promotion and now he's doing a different job? How would we, like, account for that? Make sure that, would they hopefully account for it in, like, the experiment, or that,
So we'd have to assume that things like that don't happen for employees like these. Yeah, like no one's getting any promotion during the course of this trial. Like they locked in, they signed a document, like you will stay with the company and be okay with not being promoted or demoted or anything like that. And still do the same job, you know what I mean? It's a good question. All right, so degrees of freedom equals 10. Can you guys look at your table and tell me what some of the numbers are around the negative or positive 2.86 neighborhood? So what are they in that 10 row? 2.764. What was the one on this side, just for reference?
2.35.
You guys see that one? Actually, we know how to read this by now. Yep. And the next one is.
169.
So, if those are the values in the 10-degree row of the table, then our thing is right in here, right? So that's where our p-value will be. So what are the two p-values up here at the top for these guys?
0.05.
For this one, it's what?
It's 0.00.
0.02? And this one's point. Trusting your guys' know.
0.005 and 0.01.
So this is 0.01,
Yes.
and this is 0.005. Is that right?
Yes.
Yes.
We're going to check it here with our calculator in a second, but it sounds like that's what people are talking about. So find those values on your t table, and so that means that the p-value is going to be between 0.005, because we had a one-tail test, not a 2, right? If it was 2, you just double them just like always. And what do you guys think? Should we reject or not?
No.
Pretty darn small, so I'm going to say reject. So conclusion. We will reject H sub O with such a small p-value. There is sufficient evidence to suggest the true difference is less for the, and here's where you have to really go back and see which way you did it. Now I've erased the data, so the true difference is less for which group. Which way did I do it? I think I went
4-day minus 5 days.
the 4-day minus 5 days, so it'd be for the 4-day, right? So is less for the 4-day week. So that's something on a paired test you've always just got to make sure you don't say it backwards, and it's easy to say backwards. So that's it. How much? You could do a confidence interval the same kind of way. You just have to go over here, make some space, and do your confidence interval. So if we wanted to do a confidence interval, it would just be x bar of the differences plus or minus t star. Let's say we wanted to do 95% one, and 10 degrees of freedom. And then that would be times Sx sub d over the square root of 10. We can get that as well. I'm just going to confirm all that stuff with my calculator here. So since I've got it in there, I might as well check my p-value is correct and all that stuff. So I'm going to go to stat tests. And what should I do here? Should I search for a paired test? What should I look for? Just the regular t-test, right? It's a one sample t-test. I've got data. You could enter your statistics, right? Like we have that too, but this is going to be faster. We wanted to compare against mu being 0, right? And we wanted to look at list 3, the differences, and we had a less than, I believe. So let's calculate that. And I think you'll see that the t-statistic we just had was the same. It's negative 2.8. The p-value is 0.008. Is that in the range that we had? Sure is. Leads to the same conclusion. And you can get confidence interval just as easily. So I'll go stat, tests, go down to the bottom where my intervals are. I need a regular t interval. Again, I'll say data, and I said 95%. So here we go. So our confidence interval, if we do that and plug in the numbers, is going to come out as negative 1748 to negative 216.4, which does not include 0, so that confirms that we should have rejected the 4-day week. Did indeed produce less mileage. So is it worth it for the health department to maybe go to a 4-day week? Sounds like it. That's got more in it than just statistical significance, right? We've decided with 2 different methods, this is statistically different. The 4-day versus the 5-day. Does that mean it's worth it for them to go to it? See, that's where you really need the confidence interval. We're 95% confident that they'll have a mileage reduction of between that much, quite a bit, to that much. That's not that much. So what we might need to do here is make this interval smaller. So how could we do that?
Make it 0.01%.
Go 90% maybe? Maybe that would be a good choice. Sacrifice a little confidence in order to get a more precise estimate, because we're still not sure if it's practically a good decision. So let me do a t interval one more time. And this isn't like a life or death decision. Maybe it'd be okay to go even down to like an 85% interval or something here. Calculate that. You can see when I went down to even an 85% interval, that's still only like 400 though. And now we know it's definitely not going to be what we hope down here at the like really big reduction, really big money savings. So is it a practical decision for this company to go from a 5 to a 4-day? That's where you've got to consider other factors, like is it going to cause people problems with their kids' daycare? Is it going to cause the company other problems? Remember that difference between practical significance and statistical significance. You have to make both of those part of a decision in the real world. I'll see you next time.
Adios, hedgehogs.